Alright everybody, so in this video we're going to go through how to set up reactions and reactor design in Aspen. And since we haven't yet had in your classes anything to deal with reaction kinetics in its full form, you'll get that in CME 550. We're going to really focus on simpler systems, stoichiometric reactors, where we actually have a given extended conversion that we can use and then do mass balances around that to handle this. In addition, we're going to look at sensitivity analysis, how we can use Aspen to answer important questions and have it iterate for us rather than having us to guess and change things over time. And then finally show you how recycle loops can be handled in Aspen and interpreting results from these. So really briefly, Aspen is actually quite powerful in the kinds of reactors it can set up. Here's an example of a data set of the type of reactors it can take in. Our CSTRs and plug flow reactors, you'll get these in reactor design. You'll see you can also set up a equilibrium reactor, or like I said, a reactor where we have an unknown kinetics, but we know the stoichiometry of the reaction and the extent of reaction, so we'll use this one. And the model that we're going to use today, the model reaction as an example, is going to be the conversion of or production of styrene. We can look at as a common monomer for generation of styrene or common reactant is that of ethylbenzene. We're going to convert ethylbenzene into styrene through a dehydration reaction. This is an endothermic reaction, so it's going to require heat. A lot of this heat can come from the temperature of the stream coming in, but if we end up having to have excess conversion, that heat will have to come from somewhere else. So, and then finally, the conditions in this reactor that we're going to say is we're going to assume a flow rate of 880 Kelvin and a flow rate of 217 moles per second. And we're going to specify ethylbenzene is converted from styrene and hydrogen in the reactor, and it's going to convert at 80%. This is just given, and this is the reaction that we're going to use. And notice they're all equal stoichiometry, so 1 mole of ethylbenzene will produce 1 mole of styrene and 1 mole of hydrogen. And the reactor will initially be run at a lower temperature, 250 degrees C. All right, at isothermal conditions. So with that said, let's go ahead and start our setup. So I'm going to say new. We're going to do general with metric units, create. And in this process, we're going to go pretty fast now because I'm going to assume, I think that you've got the handle on how to really begin setting these up. So we're going to start by doing a search for ethylbenzene. Find now. Yep, there it is. Double click that. Close, and we can go find the next one. We can do styrene. Great. Close. Find next, and we can do hydrogen. And we are good. Good. Close. And like always, Aspen makes these names terrible, so let's change it to something that we can actually understand. So we'll call this ethbenz. Rename. This will be styrene. Rename. And this will be H2 for hydrogen. Rename. Great. Now we have methods. The methods base set that we're going to do, this is a oil industry one, so if we want we can go down to the oil gas, and it doesn't have the one I want in there, so I'm not going to do that. But let's just go to general, because what I really want to use is the Pang-Robinson system. That's a nice one for hydrocarbons. So we'll use Pang-Robinson equation of state, and now the properties are all satisfied. So we can go to simulation, and we can start setting up our flow sheet. The first thing we're going to do is go to reactors and put in our stoichiometric reactor, our stoich. We're just going to drop that in, and now we can add in our materials. And our material feed is going to go in there, and our output feed is going to go there. Now you'll notice I have a habit of making little jaggies because they don't always line up like I like, but I can re-click this, and if I say align blocks, it'll make them nice and straight. So if you've been wondering how to do that, that is exactly how to do that. So we can relabel these. Feed, product. You always want to label your streams. And B will be reactor, because I am a clever namer of stuff. So there we go. Reactor, block, and so forth. And like I said, if this is too small for you to see, you can always do the wheel to zoom in. And that will make this a little bit easier to read. There you go. Good. So now that we have the reactor set up, we have our next step. I'm going to click next to go to the next stream input. Now, we specified 880 Kelvin as our input temperature, and the pressure was 1.378 bar. And this was in moles per second. So we're going to go to mole per second, and 217 moles per second. And the mole fraction of our stream is going to be 100% ethyl benzene. So the stream is fully satisfied. Now we have to go to our block, and this is a new one for you, so we'll go a little bit slower. In this case now, we're going to specify the temperature of the reactor as 250 degrees C, not Kelvin, but C. And here, this is going to be the same temperature of 1.378. And now we have to specify the reactions. And here, this is where we get to enter in the stoichiometry of our system that we wanted. Now, if you remember, we can say new, and we get a nice little stoichiometric window that pops up. Here we can enter in the components that are on the reactant side of the reaction. So ethyl benzene, and then styrene and hydrogen are our products. The only thing we have to now fill in is our coefficients, how many moles of ethyl benzene are required to convert into these. Aspen doesn't know the stoichiometry inherently, so you have to tell it. So I can say 1 mole is going to be converted. Now, when I'm done with that, you'll notice it automatically puts a negative sign there. I could have added it, didn't need to, but you just know reactants have to be negative because they're being consumed. In styrene, these are all 1 mole to 1 mole to 1 mole. That's good. And as I stated, the reactor we're going to assume has a fractional conversion of 0.8 ethyl benzene. So what that means is 80% of all ethyl benzene entering into the reactor is getting converted into styrene and hydrogen. We can say close, and we are good. Let's click next. It says all inputs are now complete. We can click OK. It ran. It said no issues were found. Yay for us. Now we can go to our results summary. And in the streams you can see, oh, and I forgot, we wanted to see mole fractions, and it didn't give it to us. So we have to go back up, go to report options, go to streams, and say, I want all of this. I just want to know it. I want to know mole fraction and mass fraction of our streams. Click run again, go to streams, and sure enough, we have the mole fraction, mass fraction, and mole fraction of our streams. Very good. Now just notice the stream coming in, since we have 80% of the ethyl benzene being converted into styrene, then that means in the mole fraction standpoint, what's leaving should be 20 mass percent of ethyl benzene, and the remaining 80% mass percent should be from the styrene and hydrogen, because all the mass that was converted from ethyl benzene, 80% of it went to create the mass for styrene and hydrogen. So that balances quite nicely, and so we're happy to see that. We could confirm this further by looking at the ratio of ethyl benzene product to the entering feed. If we did a quick calculator, bring it over here, and I just said 156.24 ethyl benzene moles divided by 781.2, and sure enough, it's 20%. So yes, the conversion is happening as you'd expect. Now the question here is, what is the heat duty happening in the reactor? Well, we can go to our reactor block, and you can look at the results, and you can see here the heat duty is 0.8 gigacalories per hour reaction. In other words, it's requiring heat from the X side, outside of 0.8 gigacalories per hour, or 0.9, to create and run this reaction. So it is a endothermic reaction requiring heat input. And so the question here is, what would happen if we ran this reaction adiabatically? What would be the results here in that case? So we could test that question by going to our blocks again, going to our reactor setup, and now instead of entering in temperature and pressure as our two inputs, we could enter in heat duty. And you see this gets grayed out. That number is no longer being used as an input. And now, if it's adiabatic, that just means our heat duty is 0. We can rerun this stream, and if all things being equal, the temperature on the output streams should be less than the 250 degrees C. And sure enough, it is. It's now 229 degrees C, meaning that we had to take more heat from the feed stream coming in to convert it into our to achieve our 80% conversion rate for this reaction. So you can definitely see this as an endothermic reaction requiring heat to convert this. Now the question is, since we can take heat from the input and put it into the product, the question becomes, well, what about the reaction if we were to run this under, say, a varied fractional conversion? If we go from 0 to 100% fractional conversion, what is the heat duty of the reactor in that conditions? Assuming the reactor remains at isothermal conditions at the initial 250 degrees reaction. So we can set that up. I'm going to go back, change the duty to temperature, and we're back to those conditions now. That's very good. And now we wanted to really check to see this variance. And we saw a little bit about this on class on Monday, or I'm sorry, on Thursday, where I did a sensitivity analysis in class. And that's what we're going to run again here now. And I'm going to go through this a little bit slower, and a little bit more carefully so that you can see exactly how to run this. Now, Aspen can run these analyses along with running the simulation through what it calls model analysis tools, which is found right here. You can open up these model analysis tools, click the little down arrow, and you have these different options. The one we want is sensitivity analysis. This lets how properties change of other stuff as we change the property of one thing. So let's enter in. I'm just going to call this S1. I don't care to give it a name idea. You can give it a different idea if you want. It's entirely up to you. Now, the first thing we're going to check here is we have to say what we want to vary, what we're going to look at once, like based on what we're going to vary, and then the table we're going to create. These are the three things we have to input in the sensitivity analysis. So the first thing we're going to vary is the extent of conversion. Now, this is the hardest part of setting these up, is always to know where the variables are located. Aspen's going to try to break them down and cluster the variables into groupings that it thinks is convenient. It may or may not be convenient for you. As you learn this, it becomes more used to you, but it can be a exercise in stress and frustration trying to figure out just exactly how Aspen wants to define things. So let's think of it in this regard. We want to look at the rate of conversion, extent of conversion of the ethylbenzene into styrene in the reactor. So this is all happening in the reactor. And if you remember, we actually had to program in this number in the reactor. So this is actually a reactor variable or a block variable. So we can go to the block variable and go there. Now we have to say what block we want to know. We have only one reactor, but if we had more blocks, they'd show up there. Once we have that, we can say what variable within that reactor we want to do. Now you can go highlight over and you can see each one of these comes up with a little bit of a description of what it is. What we want is that conversion, the fractional conversion of our components. And we selected that. And then finally, this last ID, 1, it's like, well, what is that asking us? Well, you highlight over again and it tells you it wants the reaction number for the reaction as defined in the reactant block. If you don't remember what that was, well, we can go back to the reactor block. And you can go to reactor, you can go to your reactions, and reaction number, we only have 1, so it's clearly the one that we're interested in is reactor 1. So go back here and say just 1. Good. Now overall range, we can give a minimum value, we say 0, a maximum value of 1, full conversion, and we can specify how many data points we want to look at, or what the increments between data points. Let's look at increments, and we'll do this in 0.05 increments. Now, 0.02. Let's do that. Okay, we'll get a lot more data points, but that's okay. So we have that, and you'll notice all these are now entered in. It's happy, it has everything it needs to know. Now I can go to define. This is going to be the area where we enter in and saying, okay, now that we're going to vary the one variable, what is it that we want to see changed? And we can select more than one output, one variable, a whole bunch of them. It's entirely up to you. But for our purposes, we just want to know the heat duty of the reactor, how much heat is flowing into or out of the reactor as a function of conversion. So in this case, we will call this duty. And now, what are we going to call this? So again, this is going to be a block variable because it's the block, the heat duty to the reactor. We're going to go to block variable of the reactor and the variable. Now, once again, we get the whole list of all the variables that we can report here. Now, your initial gut may be to say, oh, duty, that's what we want. But notice, this actually specifies specified heat duty, meaning this is a value that Aspen is taking in from the user. If we select this one, it's just going to be flatlined because we don't specify a variable. It's going to take it as blank or 0, and it won't change. What we want is the one that is a calculated heat duty based on all the equations once it runs the simulation. So we have to scroll down and look at this thing here. It says net heat duty or net duty. And now you see this is actually being defined as the calculated duty. This is the one we want. Why they do it this way, I don't know. But this is just how Aspen separates these two values. So now the defined, because we already have one defined, it's happy with it. So we're good to go. We can now go to tabulate, fill variables, and we can specify the column. This is useful in creating the table outputs if you have multiple output defined variables that you want. And now you can also here give table headings of what you're going to call this in these values. So the column label for this one, we'll just call this heat duty or heat dut, and units, gigacalorie per hour, because that's what it is being reported in. And that's it. So now we just click run, and we can look at the results, and we can scroll down, and you'll notice that our heat duty, as we converted, as we went from 0 conversion, we had a gigacalorie mole of negative heat duty, meaning that because we were entering this stream in at 880 Kelvin to begin with, and dropping it down to 250 degrees C, that we are losing heat from the system. So this is evolving heat, and so that the system was actually negative until we get a point of conversion where we started having to start taking heat to allow the conversion to happen. And this is the conversion point. You'll notice between 0.76 and 0.78, we went from a system that was evolving heat or losing heat to the environment to one that required heat and extra heat to get the conversion to go. If you want to see how this looks like in action, we can actually plot curves from the results. We can just go over here and say results curve. Now you'll get this little window here that says what do you want to plot, what you're going to vary, the x value, which is going to be the varied value, and then you can select the plots you want to show. In this case, this is going to be heat duty. Click OK, and well, it's just a straight line, but still, you can see this. And you can edit this, and you can copy and paste this into figures and charts and so forth. So, but this is all available to you to have. And so this is a really nice way of looking at the assessment. And you can see here, this line, this all too important 0 line, that specifies when you start needing to add extra heat to get the conversion to happen as you want. And that is how you handle sensitivity analysis. And you can see that this is a very clean and easy way of assessing these important parameters of how things change. It's a major difference between a reactor that requires you to pull heat from the system to one that requires you to add heat. And that's an important consideration to know. So let's go ahead I'm going to delete the sensitivity analysis because the last thing I want to show you, delete, in this round of video, is I want to show you how to set up a recycle loop. Now, it's very common in systems, in reactors, when reactors achieve a specific extent of reaction, you'll always have some of the feed reactants coming out in the product. And oftentimes, you'd like to actually recycle those. If you can purify them somehow and send them back into the reactor, we can get improved yields. And the question is, well, what would it look like in our reaction to do that? What would happen to our energy requirements? What would happen to the sizing of the reactor? And all these other things that we would need to know. So we can do this. So we can go to our separators and put a separator on this end. Now, of course, if we had thermodynamics that can drive the separation, that would be great. We can look at a flash unit, separate these systems based on the vapor-liquid equilibrium and so forth, and go from there. For our purposes, since it is a training tool, and if you don't have a separator that you necessarily know what can do for you just yet, you can use this sep option, and this lets you program in and specify somewhat fictitious, or maybe they're real, depending on the kind of separator you're using, values of given fractional splits. So you could actually say here, let's go ahead and connect this to the input, and then we can connect some outputs. Let's connect this here, and then you can create a recycle loop. Now, to create a recycle loop, we're just going to click that, have it connect to the reactor. Thankfully, Aspen's smart enough to say, oh, this is a recycle, so I'm going to have it go up and around. And there. Now that we connected that, I'm going to move this up a little bit more so it's easier to read. I'm going to pull this down. Oops. Wrong one. Let's undo. There we go. Let's leave it like that. Realize there are undo buttons in Aspen that you can vary as you need. I'm going to put that there. Let's move that there. Now let's do our renaming. We'll call this recycle. This block we'll just call our splitter, or split, and this can be our output, our final output. There you go. So now we have our recycle stream. You'll notice the one thing we have to specify now is our split unit. We have to specify a split fraction now. The block, like I said, this is somewhat arbitrary. If you have data from actual methodology for separations, you can enter it in here. Otherwise, you can use this as a test bed or what-if analysis to say if you have a separator that splits out certain fractions at certain percentages, what would it look like? For our purposes, we're going to say we have a splitter or a separator that can get 100% of the styrene and hydrogen out into the output product stream. But we're going to say that 80% of the ethyl benzene coming in is going to get recycled back into the recycle loop. So this is here by saying 0.2, we're saying 80% of this the separator stream is 20% is coming into here, 80% or the remainder is going to the recycle loop. Styrene, this is 1, the other one has to be 0, and same thing here. So that's the reactor, that's our separator, that's everything we have. So now we can say run, and we can now look at our stream results and see what came out of this. Now, our feed stream coming in is 606.9, our 880 Kelvin stream. You'll notice the pressures are all the same, or as they should be. But what you'll see here now is our output stream. What was our output stream when our final output went from 20% ethyl benzene in mass is now into less than 5%, meaning that we did enhance our yield of conversion by adding this recycle stream, as you'd expect that this would happen. And one of the things you can check to see is, well, did we still have the same conversion that we'd want? And the way we can check that again is just by doing a quick mass balance. You note that in this case, the recycle loop plus the feed is the input into our reactor stream, and this product is the output. So what should be is 186 divided by the sum of 781.2 plus our recycle stream, which is 148.8, and that should be 20%. And sure enough, it is. So our mole balance is being, our mass fraction is, our mole fraction conversion is maintained. Everything else works good. But now what's happening with our yields of our system? Well, we can look at our heat duty of our reaction, go to results, and look at the block reactor heat duty, and you can see that with the reactant stream, when we were at 0.98 or 0.9 originally with conversion heat duty, by adding the recycle loop, we've increased the heat duty about 4 times as a result of this, meaning that the amount of heat required to improve or get this kind of enhanced yield has gone up substantially. So you have to determine whether or not this is worth it in terms of savings and conversion of the reaction and the product yields that you'd obtain. It can be worth it. It just depends on the economics of the system. It also, because we are recycling in larger flow rates into the reactor and this system is coming out, these internal flow rates, so in other words, the product stream in this case here, mole flow went from feed of 781.2 has now gone up to 1674 mole flow. A lot of that's based on the fact that it's doubled because of the conversion and so forth, but there's a lot more material here. There's a lot more system here, so you can get a sense of what's happening with by adding a recycle loop. Just needing a larger reactor to handle this bigger flow and so forth will be part of the economic analysis you do, and you can use Aspen to calculate those as well. So with all that said, this is how we're going to stop here. One of the things we can now do, though, is you can actually go back and look at sensitivity analysis, run a sensitivity analysis to say on that split fraction, what happens if we vary the amount of material that went from our reaction system, leaving the separator, if we went from, say, a split fraction of 20%, 10%, 1%, what happens to the cost or the heat duty in our system? How much more energy is required to achieve that conversion? What's that doing to our yields as well? And that's something we can do on Tuesday in class. So I look forward to seeing you then, and have a great rest of the weekend.